Hello viewers, welcome to Geeks for Geeks. In this tutorial, we will be looking at how to find the increasing subsequence of length 3 with maximum product. We will be given a sequence of non-negative integers. Find the subsequence of length 3 having maximum product with the numbers of the subsequence being in ascending order. Let's look at an example. If the input array is this, our output should be 8, 9 and 10. This is another example. Our output should be 5, 8 and 9 in this case because it has maximum product and it is an increasing subsequence. Since we want to find the maximum product, we need to find following two things for every element in the given sequence. LSL, that is the largest smaller element on left of given element. LGR, that is the largest greater element on right of given element. Once we find LSL and LGR for an element, we can find the product of element with its LSL and LGR if they both exist. We calculate this product for every element and return maximum of all products. A simple method is to use nested loops. The outer loop traverses every element in sequence. Inside the outer loop, run two inner loops, one after other, to find LSL and LGR of current element. Time complexity of this method is big O of n square. This is a better solution. We can do this in big O of n log n time. For simplicity, let us first create two array LSL and LGR of size n, each where n is number of elements in the input array. The main task is to fill two arrays LSL and LGR. Once we have these two arrays filled, all we need to find maximum product LSL into array into LGR of ith element, where I lies between 0 and n-1. Note that LSL I doesn't exist for I equal to 0 and LGR I doesn't exist for I equal to n-1. We can fill LSL in big O of n log n time and we can fill LGR in big O of n time. We can find LSL in big O of n log n time. The idea is to use a balanced binary search tree like AVL. We start with empty AVL tree, insert the leftmost element in it. Then we traverse the input array starting from second element to second last element. For every element currently being traversed, we find the floor of it in AVL tree. If floor exists, we store the floor in LSL, otherwise we store null. After storing the floor, we insert the current element in the AVL tree. For code of AVL tree, you may refer to videos and articles uploaded by GeeksforGeeks. We can fill LGR in big O of n time. We traverse from right side and keep track of largest element. If the largest element is greater than current element, we store it in LGR. Otherwise, we store null. For code, refer to this video uploaded by GeeksforGeeks. Finally, we run a big O n loop and return maximum of LSL I into array I into LGR I. Overall complexity of this approach is big O of n log n plus big O of n plus big O of n, which is big O of n log n. Auxiliary space required is big O of n. Thank you for watching. Please leave us your likes and comments.